All right. Welcome to the May Grass Membership Meeting. Tonight's guest speaker is Dr.
Colin Turley.
I remember the name. Sorry about that, Colin.
No worries.
Turley. And I believe he's going to be talking about how space can kill you. So I'm going to turn it over to him. He's coming to us remotely tonight, so I want to turn the program over to him. And after the program is over, we'll conduct our regular business and that like. So, Dr. Colin Turley.
So, good morning, everyone. I'm here to tell you all about all the fun ways that space can kill you. Now, I was planning on giving this talk live, but then last week I had the misfortune of getting COVID. And when I did my at-home COVID test this morning to see, am I safe to be around people yet? The answer was just no. You are still COVID contagious. Do not go outside. So, in the advance of not giving anyone the plague, I will do this remotely.
And we appreciate it.
Now, I should note that while this talk is about how space can kill you, this talk is not comprehensive. There are numerous ways space can and will kill you that we're not going to be talking about today because they simply are too many of them. Space can kill you in a very, very, very large number of ways. So anyway, how space can kill you. So in essence, humans need 4 essential things to stay alive. You need air, you need water, you need food, you also need shelter from the environment. Well, space doesn't have air. That's kind of the point of space. It's not air. You also don't have water, or at least not normally. There are interstellar water clouds. They're not going to help you. They will just kill you a different way. There's no food in space. If there is, something's gone very wrong. And you have no shelter from anything because it's space. It's defined by being empty. So basically, all the basic things you need to stay alive just aren't there anymore. So, let's start to go over how space will affect you if you go into it. So let's start simple. Imagine we start going upwards in the air, upwards closer and closer to space. Well, as you get to higher and higher altitudes, a few things happen. Notably, the air pressure goes down dramatically. There's less and less air to breathe at higher and higher altitudes. Similarly, the air gets colder and colder and colder at higher altitudes. Yes, there's some shenanigans in the mesosphere due to ozone. That's not really enough to save you from freezing to death. In general, at higher altitudes, it gets colder, and there's significantly less oxygen available for respiration. This causes several problems for people because, once again, you need air to survive. Duh. So, what happens at high altitude? Well, as you go to higher and higher altitudes, there's less and less oxygen available, so eventually you start to encounter what we call hypoxia. Basically, not enough air. Here's a chart, and this chart shows you basically the different effects you'd have on your body at different altitudes. Basically, they do this is enough in increments of like 5 to 10,000 feet because that's how pilots do it in America. But basically, the gist of it is that you have a bunch of different bad things that happen to you at higher and higher altitudes. This is why if you're on a commercial flight and they ever lose cabin pressure, they drop oxygen masks because you need oxygen to survive, and hypoxia is very, very deadly. But it's easy to fix too. You give them oxygen, they're fine. If you go above 26,000 feet of elevation, the oxygen levels get so low, people can't survive even at all. You will just, while you can go up there a little bit, you will die very quickly. Not a good place to go. Basically, if you go too high up in elevation without supplemental oxygen, you die. Painfully. It's a slow death. Now, climbers at high mountains supplement themselves with oxygen to do this. Though I should note that some climbers have decided to climb Mount Everest and K2 without supplemental oxygen. And unless you're like a Sherpa, doing this is a bad idea because you tend to get brain damage in the process. So yes, you can say you climb Mount Everest without oxygen. You also got some brain damage in the process. If you're a Sherpa, don't worry about this. You have a completely different lung system that is highly resilient to hypoxia, and well, that's less of a problem. But most of us are not Sherpas, ergo, if we try going up this mountain with oxygen, we'll probably get brain damage, and quite a bit of it. Details. I guess bragging rights involves brain damage. All right. Anyway, other thing happens at higher and higher altitudes. In addition to there being less oxygen, there's less air pressure. And at some point, at very, very, very high altitudes, the air pressure is so low, water boils at body temperature. For example, when they crewed planes like the SR-71 Blackbird or the U-2 Dragon Lady, those planes flew at such high altitudes to keep the pilot's blood from boiling off. They had to wear pressure suits. Basically, it's not good to have your blood boiling or your saliva boiling off your tongue. I know of one case where this has happened to a person accidentally. Back in the 60s, NASA was doing a spacesuit test in a giant vacuum chamber, and one of the hoses came unhooked accidentally. The astronaut was in a bad situation for a little bit before they pressurized the chamber on him. He recalls feeling his mouth start to boil on the inside before he passed out quickly. But after a bit of repressurization, he was fine somehow. Though, once again, he's the only person I can think of that survived going into pure vacuum accidentally. And while he was fine, I can't guarantee everyone else who does this will be fine because, vacuum has some problems. Low pressure, your saliva boils, the fluid in your eyes apparently boils too. I'm told this is painful. I have not experienced this personally. I don't want to, but Main point is that all the different parts of your body that you're used to stop working correctly in a vacuum. So you die quickly. That's all the main stuff about dealing with what happens if you physically go into space yourself. Next thing to note, at high altitude, air gets really, 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 really cold. Above 100 kilometers of elevation, the air up there is so thin, even though it is actually quite warm at some of those altitudes, you can't feel it. It's so thin, you can't transfer heat efficiently. Basically, you can't transfer heat using air anymore because it's just too thin. So that means if you're in the sun, you might boil to death. If you're not in the sun, you might freeze to death because there's nothing to hold on heat, just radiation. And so you have to worry about now insulation in space to keep yourself both warm or cool or both. If an astronaut is in the sunny side of the space station, they have to avoid burning their fluids off. If they're on the cold side, in the dark, they have to worry about not freezing to death. So to ameliorate that, you have what we call radiative insulation. Basically, a bunch of fine layers of reflective foil act as insulation in space. It works quite nicely. But basically, that's what Webb uses, a radiative shield. It's hot on this side, cold on this side. The idea is that the sunlight gets through, and you have a big shield. Also works backwards. If this is a person over here, it can be warm here, cold here. Basically, on the sunny side of the space station, for example, it can be over 250 degrees Fahrenheit. That's, not good. The dark side, negative 250 Fahrenheit, which once again, not good for people. People tend not to handle anything much above 40 Celsius very well, and not below zero. So problems. You need good insulation, basically. All right. Next thing to talk about at altitude. You're another problem. Radiation. Basically, there's radiation coming on our planet from space. There's a long history of discovering how we found this out. Literally, at one point, a guy wanted to test if the ground was radioactive, so he got in a hot air balloon and flew up at the high altitude to measure the radiation levels at altitude and discovered, nope, radiation comes from space, not the ground. Mostly. There's some caveats there. There's a lot of history, but yeah, literally, at one point in the 1900s, Victor Hess took a balloon up in the air to figure out where the radiation was coming from and discovered it was coming from space. Now, we are very, very well protected from radiation on Earth because we have several miles of air over our heads. Several miles of air is a great shield. It keeps us from getting heavily irradiated. We also have a giant magnetosphere. A magnetic field around us keeps us protected from all the charged particles from space. If it didn't, we would be bombarded with them and we'd have significant problems. Side note, it also would kill electronic devices. Back when NASA was first launching satellites into space, they noticed that radiation tends to kill electronic circuits. So if you're running a computer in space, you have to run some very specialized and resilient electronics, otherwise your computer will fry under the radiation and stop working. Basically, you can't do anything too fancy, otherwise the sun burns it, so does space. Also, for other reasons, you can't make any electrical conductors out of tin because it grows whiskers in space, apparently. But that's not really very important right now. It's just a weird detail you get from learning about space stuff. Main point is we're protected from it on Earth's surface, but if you go to space, you're not. As your altitude goes up higher and higher and higher, the radiation from things like gamma rays, electrons, protons, neutrons, cosmic rays, all the fun stuff you don't want to get hit by just gets higher and higher and higher. So basically, you're receiving a lot more radiation up in space. And if you go outside the Van Allen belts, outside the Earth's magnetosphere, you get even more radiation. Wonderful stuff. Now, our bodies can handle a lot of radiation, but a lot is not infinite radiation. So with enough radiation, you'll develop acute radiation sickness and also death. Or cancer if you survive it. Wonderful options. So basically, with enough radiation, what happens is that the particles of radiation actually have enough energy that they can break through your skin and punch holes in your cells, somewhat literally. The basic idea of how you can get cancer is that, for example, a particle from space slides through your body, hits your DNA, and breaks it somehow. When it breaks your DNA, bad stuff happens. It can impair DNA. Now, normally, if your DNA is broken, your body realizes, wait, this DNA is not working correctly. Let's just get rid of it. And the cell will go into what we call apoptosis or programmed suicide. So normally, if you give your cells radiation, they just die. And they just nope out. But if you damage them in a very specific and just right way, the part of the cell that tells itself to die gets broken. And the cell instead becomes cancer. The exact how and why of this is still being studied. Believe me, we don't understand all that there is to know about cancer, and we're still learning more about how it works. But somehow, the parts of a cell are badly broken, and therefore they grow out of control, and congratulations, you now have the worst superpower of all, cancer. Basically, with enough radiation, you might get cancer. So you get dead from radiation from space, you can get cancer, or just, radiation sickness and death. Side note, a lot of our best data on radiation sickness and dying of radiation sickness comes from the Soviets due to Chernobyl. When they blew up a nuclear reactor, they had a lot of accidental studies on how to treat radiation sickness because, well, they had a lot of people that got radiation sickness from working on the blown up nuclear reactor. So yes, that's where a lot of our best data about radiation sickness comes from. It's kind of morbid, but details. I should also note that radiation comes in, broadly speaking, 3 flavors. We call them alpha radiation, beta radiation, and gamma radiation. Alpha radiation is very dangerous, but it's easy to block. You can block it with tissue paper. It's only a problem if it gets into your body. So if an alpha source gets in your body, you are very screwed. If it stays outside your body, you're fine. So don't eat alpha sources, basically. Don't eat them, ever. Beta sources, a bit more dangerous in some ways. You can stop them with aluminum foil. Excuse me. Still dangerous, but they can be shielded. Gamma radiation is annoying because it's very hard to shield. You need, a lot of lead to stop gamma radiation. You need a lot of shielding, which is expensive, and if it's in space, also quite heavy. I mean, lead bricks are not light. They're actually quite heavy. Lead bricks. So, yeah. Now, in space, you get more radiation because, less atmosphere to protect you. In general, in the U.S., a person receives about an annual dose of a little under 5 millisieverts of radiation per year overall. That's the average U.S. dose of radiation per year, which is not that much. My body can handle it no problem. If you're a radiation worker under the Department of Energy, you're limited to somewhere around 11 or 12 millisieverts of radiation per year. If you live on the 6 months on the International Space Station, you're approaching like 80 or 90 millisieverts of radiation per year. If you're, if you're trying to fly to Mars, your radiation levels are now well over 100 millisieverts. Spend a lot of time on Mars, also a lot of cancer. Basically, any dosage above 100 millisieverts, this line right here, is going to give you increased cancer risk. And if you receive 400 sieverts in a short period of time, you're likely to get radiation poisoning. If you get 2 sieverts of radiation, you're probably going to die. With 8 sieverts, you're going to die no matter what. Nothing we can do. My main point here is that when you go into space, the radiation levels get problematic, and shooting against them is difficult. So, for example, the trip to Mars, you're probably going to get some serious radiation doses, enough that you're going to have major problems trying to live there. In fact, anyone going to Mars is probably a one-way ticket to being dead, because radiation, also, the very dirt on Mars itself is kind of poisonous. It's made of perchlorate salts, which are toxic. Very toxic. Also, they're one of the main ingredients of certain types of rocket fuel, so also other problems. So anyway, just some notes there about radiation killing you in space. Now, even if you're not going to space yourself, space can still kill you because, space is powerful. So sometimes parts of our sun's surface just blow up a lot. For example, here's a picture of a solar flare. This is the prominent. This arc of plasma right here is bigger than our planet by a lot. This is like a Jupiter-sized arc of plasma. And you can see here, it explodes. Here's a before, here's an explosion. So sometimes parts of the sun's surface just blow up. And that ejects radiation into space like crazy. It can push the auroras further south. When this gets bad, it can push the auroras further south than Baton Rouge, which is interesting but not good. It'll trigger radio blackouts across the poles. It can knock out a power grid. As you might remember from, Texas a few years back, there are ways you can protect against power outages from weather events, but the problem is power company has to actually pay for it. And as Texas demonstrated with its ice-induced blizzards a few years ago, not all power companies like to actually winterproof or weatherproof their grids. So we could weatherproof our grid against the sun. We aren't because it's expensive, and people don't want to pay for the sun blowing up the power grid. Apparently it's too expensive to proof the power grid against the sun blowing it up. Details. So anyway, the sun can occasionally shoot out large amounts of plasma and do a bunch of damage on the Earth, which is a problem. Our atmosphere also protects us from physical objects, like meteors. A lot of meteors, they're just basically rocks that fly through the sky and burn up in the atmosphere. All good and safe, producing nice streaks of light in the sky. But they also are actual rocks falling through space, and those rocks can cause damage. Not normally. Most meteors are just light shows in the sky, but it is possible for rocks from space to cause serious damage on the ground. Now, you might think that, you might get killed by a falling meteor, except that we have no record of this ever happening. There's no record of a person ever being struck by a meteor. Or at least there's only one record we have of a person being struck by a meteor, and she survived no problem. She was apparently sleeping in her chair in her house, and a meteor grazed her side. She had a nasty bruise. Also, because of reasons, the U.S. government confiscated the meteor, and she never got to sell it. So yeah, she got hit by a meteor, had to go to the hospital, and then the U.S. government confiscated the meteor from her house, despite it having fallen into her literal living room. I know, weird stuff. The main point is that, while no one we know of has ever been killed by being hit by a meteor, you could definitely get damaged by them pretty badly if one were to hit you, because they're moving at quite high speeds. At fast speeds, even like single pellets can become deadly projectiles, making huge splashes on the ground. Excuse me. In fact, at space speeds, even flecks of paint can be dangerous. Like this is a picture of a window in the International Space Station. It got hit by a microscopic fleck of paint traveling at 17,000 miles an hour. It cracked the window in place because the fleck of paint moving at 17,000 miles an hour. So if you go to space, even the dust particles can be moving fast enough to seriously hurt you, which is the scary thing to think about. Other things can happen? Well, meteors might not hit you, but some meteors can do a thing called become a fireball, where they basically blow up. Sometimes a meteor going overhead blows up, making a big fireball. This can cause property damage. It has before. There was a famous case like 2013 over Russia where a meteor was passing overhead and it just blew up violently. There's the famous what's it again? So there's a famous event, the Tungusia event in 1908, where a meteor blew up and flattened a good portion of Siberia. Basically, sometimes a meteor can blow up and make a huge mess in the sky. This has not been documented actually killing anyone to date. There's some legends of it killing people, but the thing is, there's legends of a lot of things happening. Like, there's legends of people being killed by meteors. But there's no actual confirmed evidence of this ever happening in the real world. Side note, there was a Greek playwright who was killed by, not a meteor, but killed by an eagle dropping a turtle on his head. The Greek playwright Aeschylus was famously killed when an eel dropped a turtle on his head. And that, there are claims of him being killed by other things too, but that's the main story is that he got killed by an eagle dropping a turtle on his head, which, it's a weird way to have. That's a weird way to die. He had a bad day, and an eagle decided to make it worse.
Well, the eagle didn't get its lunch, so,
Yeah, problems. All right, anyway. Now, if a meteor is much bigger and hits the ground, it can make a massive, big crater. Now, you might see the crater and think, I'm only in danger if I'm near the crater. If I'm far away from the crater, I'll be fine. But that's not really how things work, because if there's a massive crater, things go badly for you no matter how far away you are. This is the Behringer crater right here. It's about 1.2 kilometers wide, and it's about 50,000 years old. It's just, example of a time where a big meteor struck the planet and made a mess. And generally speaking, every once in a while, a meteor strikes our planet, and bad stuff happens. How bad? Well, the most famous I can think of for this is probably the dinosaur-killing impact, where a big asteroid hit the ocean right here and messed with the planet. Basically, everything on the planet in this red circle would have been vaporized instantly. Everything in the black circle would have been instantly killed by the pressure of the impact. Everything in this circle right here would have probably had its eardrums ruptured by the pressure of the impact. Everything in this circle right here would be the circle where you can still break glass. Basically, that impact would have been strong enough that it happened in Mexico, could have broken glass in Africa. Yeah. And the thing is, it doesn't just cause a big blast. It also causes earthquakes and tsunamis. And a lot of the stuff that gets vaporized gets pushed up into space. So suddenly, you have a bunch of flaming debris in the air. So when a big asteroid impact happens, the air catches on fire for a few minutes, possibly in a few hours, maybe even a day. And now you might be able to survive the impact if you're far away, but the thing is, what happens if the air catches on fire temporarily? That's not good. So, problems. And once the air's on fire, everything around it's also burned. All your crops are burned. Climate changes. You effectively have a nuclear winter coming up because of all the burning stuff. So, massive asteroid impact can seriously impair the planet. Side note, it is possible to actually have a supervolcano trigger an asteroid impact. We call it the Verne shot. Basically, supervolcano launches a bunch of rock up into space. The rock falls back down and hits the planet, giving an asteroid impact. We think it's happened at least once in Earth's history. But we're not quite sure when, because, hard to say that actually happened. Either way. Impacts happen, they cause damage. A lot of things die. Impacts go through, you get dust into space, you get fiery debris. Excuse me. Not a good time to be alive. All right, next thing to talk about. In addition to talking about asteroids, the next thing to talk about going to kill us is the sun. You see, the sun is a giant ball of plasma fusing hydrogen into helium. And in the distant past, it was mostly hydrogen and a bit of helium at the core. But over time, the hydrogen gets burned into helium, giving there's more and more helium at the sun's core as time goes on. So what happens as that goes on, eventually the sun will run out of core hydrogen to burn. And whenever stars run out of core hydrogen to burn, they change. Excuse me. The main point I make here is that as a star burns up its fuel, the star's core shrinks, contracts, and gets denser and hotter. So, as a star gets older and older, it tends to swell up. It gets hotter, and it swells more and more. So right now, our sun is 6% larger and 40% more luminous than it was when it formed 5 billion years ago. And as time goes on, it gets bigger and bigger and bigger and more luminous. And that means, for example, in 1 billion years, our sun will be 10% more luminous than it is now. And that means it'll be hot enough to start boiling our oceans off. So even if we do nothing, the sun will eventually get hot enough to burn our oceans up. It'll take a while. It's not happening overnight. It's not going to happen for at least 1 billion years. But still, the heating of the sun means that eventually this planet will be rendered sterile by the sun, one way or another. So, we got a calendar. We have to solve our problems in the next 1 billion years. Otherwise, oceans boil off. We have problems. As you might guess, losing oceans is not good. Similarly, once the sun runs out of core hydrogen, it climbs the red giant branch and gets really, really, really big. I'm not going to go too deep into the details, but the basic idea is that when the sun runs out of core hydrogen, it swells up to be humongously, bigly huge. And then it goes up and does some other stuff and basically fizzles out. Thing is, the sun is going to get about 100 times bigger than it is now. And eventually, then it's going to die. When it does, it's probably going to, if it's not going to swallow Earth up entirely, it's going to at least going to render us sterile. So if somehow life survives the sun getting hotter, it won't start the sun swelling up because we're probably just going to die from that no matter what. So in other words, given enough time, the sun will completely kill everything around it. I mean, it's not for a while, but not for about 5 billion years, but still. So in other words, living near a sun-like star will eventually kill you. The key word there being eventually. All right, onward and forward. Similarly, stars in space can blow up. Stars like to blow up sometimes, you see. Simple way? Well, a white dwarf, for example, a dead star, can accumulate matter. You can accumulate material from a nearby star, spiral into yourself, and eventually that material can catch on fire and blow up. And this can lead to what we call a nova. So if you're in the wrong spot of space, and the nearby star decides to blow up, you can have a problem because suddenly there's a big burning star nearby that wasn't there before. The energy from these novas can be quite intense. And if it crosses a different limit, you can even get a supernova, which is all that but worse. Basically, stars can sometimes blow up, and when they do, if you're nearby, it's not good. A nearby nova would be bad for us. It would cause problems. And if you get what we call a supernova, that basically involves like two white dwarfs merging or other things like that. You could end up with a massive explosion, and that explosion is so powerful, it is a bit frightening. When supernovas go off, they are scarily big. And if they do go off, it'll be a problem for us if one happens too close to us because, I mean, well, they're really, really bright. Famous example of a supernova actually was the supernova of 1054, the Crab Nebula. So in a supernova, generally speaking, what happens is the stars basically builds up a bunch of different layers of material as it evolves, different layers of material around itself. Eventually, you end up with what we call the iron core. Now, iron's a great material to build with, but it's not a good material for a star because you can't get energy out of iron. Iron's an energy sink. You can only dump energy into it. You can't get energy out of iron. If you try to get energy out of iron, it doesn't work. So, when large stars build up their cores, eventually they get stuck with a core of iron. They can't do anything with that. They get stuck with one. Eventually, that iron is such of a problem, the entire star blows up rather than have to deal with the problem. So the whole star blows up, iron gets, and they create a bunch of cool things. The problem is they blow up violently. They can be, they can have the luminosity of several thousand suns and leave behind special remains. This is a picture of the Crab Nebula. It was produced when a supernova blew up in 1054. The remains of it are still luminous to this day, over almost 1,000 years later. And yeah, and when the crab blew up, by the way, this was far away, and it was so luminous that the Chinese astronomers could talk about seeing it during the daytime for a month. They saw it at night for like over a year, too. Basically, these can be brighter than 10 billion stars. And that's a problem because if one happens nearby, that light level can literally burn our planet up. Badly. Which, not good. Having the planet catch on fire isn't good. So if we're too close to a supernova, we catch on fire. And we're all dead. Oops. And similarly, if the star's even bigger, it can collapse right into a black hole and create a gamma ray burst, where basically the star becomes a black hole in the middle. Now you have a black hole accreting matter inside a dying star. That causes problems, like a gamma ray burst. You can basically have prompt emission of gamma rays sprayed outwards in a giant beam towards everything else. The prompt emission of a gamma ray burst can put out a frightening amount of energy in a short period of time. Basically, if a gamma ray burst were to happen nearby and be aimed at us, it could essentially be like having the Hiroshima bomb going off every 5 feet on our planet, which, wouldn't be very good for us overall. Now, fortunately, these don't seem to happen nearby for a good reason, but if they did, there's not much we could do. It'd just be death from space, and a lot of it. Now, given all things, even though that space can kill us in fun ways, one thing that's also certain is that space will one day end. Space doesn't last forever, so one day the universe will die. There's a few different theories on how it will die. The main three explanations for how the universe will die are what we call the Big Crunch. Basically, space expands and then goes back in. When it does so, it crunches back down into a small ball and everything gets crushed. That's one possible ending. Space collapses back in itself and we all get crushed. The current thing we seem to be on is what we call what's it called? Heat death, where space is expanding and cooling off, expands and cools, and it'll just keep on cooling until it freezes over. Everything freezes, and death happens in like 100 quintillion years. So, given enough time, space will freeze and the universe is over. And a last example is what we call the Big Rip, where space expands so fast, space breaks and everything stops existing. Which is an oops if that happens, but probably not going to happen. But there's a fourth scenario that is called vacuum decay, which is, in my view, the most interesting way that space could kill you. See, in vacuum decay, unlike the previous examples where space catches on fire and we're all dead, in vacuum decay, it's more like the laws of physics themselves catch on fire. You see, there's a way that the laws of physics can decay from their current state to a different state. If that happens, basically everything, the laws of physics catch on fire, the universe burns down, and we all die. And not only is the universe gone forever, the laws of physics are burned up too, so we have to write new laws of physics to describe the universe again. So, problems. The universe is all dead. So those are some of the ways that space can make you dead. A lot of fun stuff. Thank you all for your time. Please ask all the questions you have.
Thank you.
Apologies for not being present. I like to say I didn't want to give everyone COVID.
Anyone have any questions?
I guess we're not live here live. We're all dead.
That sounds like either everyone's dead.
There's something to be said about being completely wild and just taking it back and having to contemplate your existence and then remembering that, wow, your existence is contingent upon things that are basically contingent themselves. And I'm still just baffled by vacuum death. But that seems to be like the type of thing where gravity doesn't work anymore. And so basically the reason the universe ends is just because matter.
Scott, I can barely hear you. I can't really hear what you're saying very well.
Oh, sorry.
Ends in space.
No, basically the idea of the vacuum death is one of those ones that just absolutely baffles me. It's kind of interesting. If I'm understanding it right, it's basically the laws of physics themselves break down. So like the reason you would die would be essentially that, matter doesn't make sense anymore because the rules change.
Yeah, the basic idea is that it's actually twofold. One is that when physics for physics to change like that and decay, it would release a frightening amount of energy. Like every bit of space would be simultaneously on fire because of all the energy released. And two, afterwards there'd be different laws of reality. Like the laws of that govern how space works would be different somehow. Whether or not this can even happen is still up for debate. So we don't really know for certain.
Well, and there would be no possible way to know, would there?
Yeah, this isn't something we could test.
Yeah.
I mean, not also if we could, it might be dangerous. Can you test blowing everything up?
Let's destroy the universe and see if it works.
Well, I remember of a line from Pratchett where he theorized, what if there was a cave with a lever on it, leveled universe-ending lever, do not touch. He theorized that people would actually, that if you put that sign on the lever, someone would push it just to see what happens.
Yeah, I think that's pretty much right on. I think there was another version of that it's, amateur psychology is that you don't really need a big switch, a master switch to the power switch, or a regular old light switch will work, but they decide to make it bigger so that people would be less tempted to pull it. No.
My favorite example of something like that, there was an art installation at an art museum was basically a giant metal pole with a big label that says "Do not touch" on it. But you can clearly walk up to it, even though it's clearly marked "Do not touch." You can go up and touch it. If you do, you get electric shock. Basically, people constantly walk up to it and touch it and get electric shocks. Despite it being labeled "Do not touch" and has big warning signs all over it saying "Do not touch." But the point of it is that people will see that and think, let's touch this thing. And then it goes zap.
I think it'd be great if you could put one of those on campus and then just add a counter and make sure that you can keep track of how many people will actually touch it over time.
My ninth grade freshman high school science teacher left charged capacitors on his desk with "Do not touch" signs. And in every single class, someone touched them. Nowadays, of course, you get fired if you did that. I thought it was pretty cool.
They learned that
Yes, they learned a very important lesson.
He was the inventor of the taser.
I don't know, but they were not a small dose. I did not touch one, but I could tell from the people who did. It was,
Pastors can have a pretty strong punch.
oh, yeah. Well, we used to string together a human chain off the Van de Graaff generator and hold it on the doorknob of the class. So when someone would grab the door from the outside, a big old shark would shoot out on them. That was fun.
This may be outside the area.
I think you would enjoy death from space.
The crash he talked about was about 50 million years ago.
Which crash?
The crash,
65 minutes.
65. So how would that impact, say, modern? Like,
Sorry, I couldn't hear your question. Could you come closer to the where the sound is going to me?
how would that affect like modern plate tectonics?
He was
Like,
wondering if we had
San
a
Andreas fault could have been.
Chicxulub event today, how would it affect the
How did
modern
it affect the ones
tectonics?
we have now? Is this the
Basically, it would be first of all, everything nearby that would be completely annihilated.
okay?
So if that asteroid impact happened now, think like imagine some spot in the world is completely and totally wiped flat, and then imagine that now the air would be on fire for a few hours. So basically, everything would be on fire, and then you'd have a year without summer, for maybe even several years without summer. So basically, I'm not sure if humanity would survive that per se. Life would survive because life is good at surviving everything, but definitely it would cause a complete breakdown of everything. Because I mean, it'd be worse than setting off the biggest nuke in the world in any given location.
But I mean, I guess he was asking if it would crack the mantle.
Or
No.
did it impact the plate tectonics, like fault lines we have today?
It would certainly cause other earthquakes in other places, but I don't think it would actually impact.
Okay.
I don't think it would long term change plate tectonics that much.
Okay.
And there is actually,
super volcano though.
yeah. And I think he was saying that there is
pretty
one
much
that,
into the food supply.
I have a question. Was there a relation between the Chicxulub impact and the Deccan Traps eruption? They happened about the same time.
Are you talking about the Siberian traps?
Yeah, no, the Deccan Traps in India.
I don't think they're related, but I don't know for certain. I don't believe they're related, but they could be.
About the same time. I was just curious.
What I've read lately about it, Chris, was that they are looking into it could have affected each other, possibly with also a super volcano involved on it, but they have not gotten anything to show
Okay.
or prove that they were actually related to each other yet. But that research I've read about that, it was about a month or two ago, I read something about that. That's all I can say on that.
Also, the thing is, we don't know how close they were in actual time. Like, if did they happen at the exact same time, or was it if they're off by a few decades, that would have been that would have been close. If they're off by a few decades, that would be, the causal link would be a little hard to establish then.
I think it's like about 1,000, maybe 2,000 years possibly between them, but they don't know one could have affected the other over the period of time. Just if you want, Chris, I'll try to look up that latest research I
I
read.
read some articles that were suggesting it may have had a
Okay.
Yes, it's possible, but it's currently the answer is we're not sure. It's not impossible. Almost certainly, a massive asteroid impact would cause volcanic eruptions.
I don't want
Volcanoes. It'd have secondary earthquakes. That would definitely happen. The big question is how big would those actually be overall?
I got one other question. Is there a safe space on the ISS for solar flare radiation?
I think they're close enough in that's usually not that they're usually they're close enough into Earth's magnetosphere that they're not too bad off.
So they think they would not have a problem if there was a large CMA.
I think that they're enough in Earth's magnetosphere that
Okay. They're only 442 miles up, so it's not that far.
They're still protected by the magnetic sphere.
Oh, yeah.
I'm not aware of any specific bunker they have there. Bunkers are hard to build.
Yeah. When the Carrington event, they saw the Aurora Borealis in Havana, Cuba. So that was a pretty big one.
Yeah, that was an interesting event.
Hey, we got any other questions here?
Formerly, being left out an important one.
What's that?
Maybe our next door neighbors up at Office of Jury don't like us.
Uh,
That'll be death from space from the
That's true.
Well, no, that'll be death from Alpha Centauri.
It takes them forever to get here, so don't worry about it.
Oh, yeah, but it only takes more time to get here.
What if they're already on the way?
Well, I want to thank you.
Might have been already covered.
I'd like to thank you and appreciate you coming on and doing this
That was fun.
with your. So
It was a great
appreciate
talk.
it. So,
Thanks for having me. I'm at some point we're going to talk about I'm looking at people talk, but hopefully I'll be healthy for my next talk.
Love to see you in person. All right, we're gonna go ahead and kill the stream, I think, and then
Colin, for a meeting or anything, but you don't need to stick around if you need to go.
I actually kind of do need to go though, because still sick, so I'm still working on that.
all right, we'll get better, man.
Yeah, thank you.
Thank
See
you
you all
again.
in the future.
Thank you so much.